Do you think that computers one day can solve any problem in the world? The earliest of computers could execute 200 instructions per second, and nowadays, your own computer can handle around 346,350 million instructions per second. So surely there is a point where we can compute anything, or at least have a so-called magic ball, which can say if this problem has a solution or not. Imagine all the possibilities in math and computer science if we had this power. We can have much more reliable and secure software programs, better debugging tools, far more complex systems, and a lot more potential in the systems that we are able to build. Today, hopefully you can get an answer to this question. Obviously, it is impossible for us to run through every single problem because there are so many already, and countless yet to be discovered, so we have to prove this problem using other means. Let us set the scene first. You're a software engineer who designs computers to solve problems given by your clients. You make two computers, which are perfect at what they do. One adds any two real numbers together, and the other provides the binary form for any combination of letters, computer A and computer B. The exact manner in how they work isn't important for us right now. If you input any two real numbers into computer A, you will always get the exact addition of those numbers. And if you input any combination of letters into computer B, you will always get that represented in binary form. Now, what happens if you input two numbers into computer B? What about entering a letter into computer A? We get no output for both of these cases. Why? Because the computer was obviously not made to solve for that input, and thus will be running on a continuous loop without giving an output. So now you know that your computer can either solve or not solve a problem, depending on if the input values cause the algorithm to get stuck. Now, you make a computer H, which, with given input values and the exact details of your previous problem-solving computers, returns if they get stuck in an infinite loop or not. What happens if we input 2 plus 2 into this, with computer A? What about the letter A? Our computer H always prints the right answer as it sees if the computer is stuck or not. This will allow us to see for what inputs will the computer that you have constructed work for and what inputs it won't work for. You get a bit interested and decide to delve further, seeing if you can find a computer for which it is unknown if there is a solution or not. Let us add another computer, computer C, to computer H. Computer C's only purpose is to reverse the result provided by computer H. So if computer H says stuck, computer C will return not stuck, and if computer H says not stuck, computer C will return stuck. Now, let's add a duplicating computer named computer D, which duplicates the input so that it gives the same thing as input for the computer details and values into computer H. Let's package this entire system into one computer named computer E. Now, what will happen if we input computer E into itself? Computer D will duplicate this so that it goes into both the input for computer and input for the values into computer H. So essentially, computer H will be seeing if inputting computer E into itself will result in a solution or not. Let's just say computer H results stuck. So if it thinks that inputting computer E into itself will result in a loop without a solution, then computer C will return not stuck, as it returns the opposite of computer H. Thus, the output for computer E is not stuck. But wait a second, didn't computer H just say that this will return stuck? What about we see what happens when computer H returns not stuck instead? Then C will return stuck, meaning E returns stuck overall. A contradiction. Here, we can clearly see that there is a computer out there for which we are unable to tell if there is a solution or not. The halting problem. There will always be a combination of input and output for which is undecidable for whether or not there is an output using a system like computer H. David Hilbert thought of this question. Is it possible to determine if any logical statement that we are provided with is either true or false? Alan Turing proved this using a similar proof, which basically states that any such algorithm can be made to produce contradictory output and therefore cannot be correct. Through the use of Turing machines, Turing used a paradoxical contradiction, as we saw earlier in our example of a software engineer, to show that the halting problem is undecidable, meaning that there is no algorithm that can correctly determine whether any arbitrary program halts or runs forever. Turing's work on the undecidability of the halting problem was a groundbreaking contribution to the field of theoretical computer science. His work has remained as the foundation for our understanding of the limits of computation since his time in the 1930s. Various fields of computer science, including complexity theory, practical software engineering, cryptography, and much more, have all been heavily influenced by this proof of Turing. But hey, that's just a theory, an algo theory.